Welcome to lecture 6 of module 4 of this course Game Theory and Economics. Before we start this lecture, let me take you through what we have been discussing in the last lecture. So, what we have been discussing is various aspects of mixed strategy Nash equilibrium. We have first defined mixed strategy Nash equilibrium and looked at certain properties of it. For example, that in the mixed strategy Nash equilibrium, in a proper mixed strategy Nash equilibrium, the actions which have positive probability attached to them will all have same expected payoff, and that expected payoff is the expected payoff to the player from that mixed strategy profile. And we have also, and the actions for which the probability attached is 0, the expected payoff should be at most the expected payoff to the actions where positive probability is attached. This important property of mixed strategy Nash equilibrium helps us to find the mixed strategy Nash equilibrium in different games, even if there are more than one action, more than two actions of a player, or even if there are more than two players in a game. Subsequently, we have been discussing also the modification that is needed of the concept dominance, the fact that an action can be dominated by another action, it can be strict dominance or weak dominance, that we have discussed in case of PO strategy where no randomization is allowed. But if randomization is allowed, if player can play mixed strategies, then we have seen that that definition needs to be modified. But qualitatively the game does not, the results do not change much, in the sense that even if we have mixed strategies, then it is seen that the action which is strictly dominated by another mixed strategy, then this action which is dominated will never be played in the mixed strategy Nash equilibrium. And even a mixed strategy which assigns positive probability to an action which is strictly dominated will not be played in a mixed strategy Nash equilibrium. And talking about mixed strategy Nash equilibrium and dominance, strict dominance and weak dominance, we have seen that if we have strict dominance by not both the players, in a two-player game not both the players but one player, then we can do what is known as iterated elimination of strictly dominated actions. To take you through the example that we have given in the last lecture, this was the example. Now, you can see that M strictly dominates R. So, if R is dominated, strictly dominated, R is not going to be played in the sense that there is no circumstance under which 2 will play R, because whether one chooses U or D, it is always better to play M than R. Now, if R goes out of consideration, then look, player 1 now has a strict dominance. U strictly dominates D. This is a sequential thing. Initially, U was not strictly dominating D, but since R has gone out of consideration, then this column does not matter anymore, and if this column does not matter anymore, then U is strictly dominating D. And so, now D is going out of consideration because 1 is never going to play D, and if that is the case, then 1 is left with U, and basically 2 has to choose whether he will choose L or M, and obviously 2 is greater than 1. So, M is chosen by 2 and U is chosen by 1, and 1 2 is the payoff to the players. So, this is known as iterated elimination of strictly dominated actions. Now, this may seem a very simple way, but it is not that simple as it seems. The logic is a little bit complicated. When we are eliminating these actions, what is needed is that both the players are rational, they want a higher payoff than a lower payoff, but it is not sufficient that I know I am rational. What is also known, what is also required for this elimination, this process of elimination, is that I know that the other player is also rational, and vice versa, the other player must be knowing that I am rational. So, rationality is a common knowledge, and only then we can go on eliminating the actions in a sequential manner which is strictly dominated. So, it works in the following way. Firstly, player 1 knows that player 2 is rational. Since player 2 is rational, that is why R is not going to be played. If R is not going to be played, then 1 thinks that U is better than D. Now, the fact that 1 thinks U is better than D, the fact that U is 1 is rational is known to 2, and that is why, since 2 knows that 1 is rational, and that is why he, that is 1, has figured out that 2 is not going to play R, and that is why 1 is not going to play D, that is why 1 is going to play U, and that leaves 2 with the choice between L and M, and 2 chooses M. So, this rationality does not apply to a particular person on an individual basis only. It must be a common knowledge that I am as an individual is rational. That has to be known to the other players also, and then only we can go on eliminating these strictly dominated actions. Now, this was the case of strict dominance. If we eliminate the actions which are not strictly dominated, but suppose weakly dominated, then can we get profiles, action profiles, which are, here in this case, for example, 1 2 is a Nash equilibrium, which we have got by eliminating strictly dominated actions. So, does it apply in case of weakly dominated actions also? So, do we get by eliminating weakly dominated actions, do we get profiles which are Nash equilibria and which are the only Nash equilibria, in the sense that in this game 1 2 is a Nash, that is U and M, this action profile is a Nash equilibrium, and no other action profile here is a Nash equilibrium, right? No other action profile is a Nash equilibrium. So, does this same feature apply to case where weakly dominated actions are eliminated? And we shall see that the same feature does not apply. There we shall see that the action profiles that we shall be left with in case of weakly dominated actions are not necessarily the only Nash equilibria, there could be other Nash equilibria also. Take the case here, this game. sorry. So, this is a game where player 1 has 3 actions and player 2 has 2 actions. Now, let us compare between T and M. Player 1 has 2 actions, 3 actions. If we take only these 2 actions T and M, then it is obvious that T is weakly dominated by M. So, T is not going to be played, right. T is weakly dominated, and if T is not going to be played, then I am left with only M, and if M is the action that one is going to take, if M is the action, M and B are the actions that one is going to take, then basically 2 has to consider between L and R, and it is obvious that L is weakly dominated by R. Okay. So, L goes out of the question, because 1 is 1 and 1 here. If M is played by 1, if 2 plays L, he gets 1, 2 plays R, he gets 1. If 1 plays B, if and 2 plays L, he gets 0. If 2 plays R, he gets 1. So, R is weakly dominating L. So, L goes out of the question. So, this goes out of the question. So, we are left with these 2 action profiles, and you can see that both of them are Nash equilibrium. So, we are left with MR and BR. So, these are the action profiles that we are left with, and we can check that both of them are Nash equilibrium. Now, here we started with comparing between T and M and eliminating T, which was weakly dominated by M. But if we started by comparing M and B, then what happens? Here if we compare between M and B, we can immediately see that B is weakly dominated by M. So, B is weakly dominated by M. So, B goes out of question, and if T and M are the actions to be played by player 1, then again L player 2 will compare between L and R, and he will observe that R is weakly dominated by L. So, in a sequential manner, R is weakly dominated by L. So, this R now goes out of the question, and we are left with these 2 profiles. So, it depends, you see both this TL and ML are Nash equilibria, but the point is that they are not the Nash equilibria which we got before, which were MR and BR. So, the profiles that we are left with, that set varies. that set varies depending on the order of elimination. If we had started with eliminating T, then we are getting these two profiles, but if we had started with eliminating B, then we are getting these two profiles. So, in case of weakly dominated actions and elimination of iterative elimination of weakly dominated actions, the profiles that we shall be left with, the identity of those profiles depends crucially on the order of elimination. But this was not the case in case of elimination of strictly dominated actions. There it does not matter which order you take, you shall be reaching an unique set of action profiles. Now, one reason why we are discussing this weak domination and strict domination with such emphasis is also the fact that in case of Nash equilibrium, remember the idea of Nash equilibrium, it is a steady state. Right. So, suppose we are talking about pure strategy Nash equilibrium, A star is an action profile such that given the other players are taking A naught I star, taking A I star by player I is optimal. So, that was the idea of Nash equilibrium, but a crucial question that has not been answered is that how have we reached this A star? It is true that if A star is reached, if this particular action profile is reached and if this action profile is played for a number of times, then by looking at the experience, looking at the previous history of the play of this game, people who are taking the action at a particular play of the game will take AI star or AJ star, whatever the actions at the equilibrium action profiles, at the action equilibrium action profile, because he knows that other players will be taking their expected actions. But the question that remains is how do we how did we get into this A star? There must be some beginning of the game at point 0 when the game is starting, and there is no guarantee that at the start of the game itself A star will be played. So, if there is no guarantee that at the beginning A star will be played, it may start with any any action profile, and from that arbitrary A, how do we get into A star? That question has not been resolved so far. The advantage of this strict dominance or even weak dominance is that to get into this the action profiles which we have got by iterated elimination of strictly dominated actions, we did not need the repeated play of this particular action profiles to say okay, this is going to be played. At the beginning of the game, at point 0 itself, players can figure out that they have to play that action profile. So, to give you a simple example, take the case of prisoner's dilemma. So, here we can see that player 1 has this as the strictly dominating action, and this is for player 2 the action which is strictly dominating the other action. There are only 2 actions. Now, this is therefore, this C and C, this action profile is going to be played in the beginning of the game itself. They do not need this CC to be played over and over again to figure out that at a particular play of the game the other player is going to play C, therefore, I should play C. So, here at the beginning of the game itself I can apply my rationality and I can play C. Another player also can apply his rationality, and right at the point 0 itself they will be playing C, and that will continue. This was the case where there was no iterated elimination, but in case of iterated elimination also the same logic applies. In the beginning of the play of the game itself, right at the point 0, by applying rationality and by applying the fact that the other players are rational, players can figure out what are the action profiles that are going to be played. So, therefore, this idea of strict dominance and iterated elimination of strict dominance or weakly dominated actions are helpful in the sense that we did not need a logic how come this particular action profile was played, because this is going to be played even if there is no history. But whereas in case of Nash equilibrium, we need this A star to be played for some period of time to justify that it is going to be played in future also. So, this is one advantage. And related to this idea of strict dominance and weak dominance, there is another idea of rationalizability. We shall call it rationalizable actions. They are also called sometimes as rationalizable strategy. Let us call strategies. Okay. So, what is the concept here? The idea is that an action for player I, suppose AI, is rationalizable for that player if that action can be played by player I given some belief of player I regarding other player's action. So, if player 1 has some belief, let us call it mu I, which justifies the play of AI in the sense that if he has some belief regarding other player's action, AI is the best action that he can take. Then AI will be called the rationalizable action for player I. Now, this logic does not stop here. Remember, when I is saying that I have some belief regarding other player's action and that is why I am playing AI, these other player's actions have also to be justified. So, other players' actions which are imputed in this mu I, they also have to be justified according to some belief of these other players. So, we go on and in an infinite regress. AI is being played because of some belief regarding other players' actions, and why these other players are taking these actions? Because they also have some belief regarding other players' actions of them, and blah blah blah, we go on in an infinite regress like that. And all these actions in this infinite sequence will be called rationalizable actions. This may seem a little vague, so let me start with an example how these rationalizable actions are found out in terms of real games. So, every player, 2 players are there, each of the players has 4 actions. Now, what I claim is the following. What I claim is that in this game A4 and B4 are not rationalizable actions, whereas A1, A2, A3, B1, B2, B3 are rationalizable. How am I saying this? Let us look at B4. Why I am saying that B4 is not rationalizable? The point about B4 is that no matter what is the action taken by player 1, B4 is never going to be played. If player 1 takes A1, then B1 is the best action, right? B4 is not being played. If player 1 is playing A2, best action for player 2 is play B2. If player 1 is playing A3, the best action for player 2 is B3. If player 1 is playing A4, then the best action, there are two best actions, either B1 or B3. So, B4 is never going to be played by player 2. So, player 2 can never justify under whatever beliefs that he might have why he should play B4 at all, at any circumstances. Since B4 is not being played in any of these individual cases, B4 is not going to be played even if player 1 mixes his strategies, mixes his actions. So, therefore, B4 cannot be justified, it cannot be rationalized under any circumstances by player 2, therefore, B4 is not rationalizable. Why A4 is not rationalizable is that this is dependent on the fact that B4 is not rationalizable. A4 by player 1 can be played, it is not that A4 cannot be played. A4 can be played if player 2 plays B4. You see, if B4 is played, A4 is the best response for player 1. However, there is no rationality for B4 to be played. We have just said that B4 cannot be played under any circumstances. Therefore, the justification of A4 also goes, because justification of A4 dependent on the justification of B4, and there is no justification of B4. Therefore, A4 is also not rationalizable, right. And what is the proof that the other actions are rationalizable? We can start with B3 for example. Is B3 rationalizable? Well, player 2 is going to play B3 if player 1 plays A3, because if player 1 plays A3, the best response for player 2 is to play B3. He is getting 7 here, which is the highest of 0, 5, 7 and 1. And what is the justification that player 1 is going to play A3? So, let me write the sequences here. B3 is being played because player 2 believes that player 1 is going to play A3. Why is A3 being played, or what is the justification for player 2 to believe that player 1 is going to play A3? Well, player 1 can play A3 if player 1 believes player 2 is going to play B1, right. If B1 is played, then best response for player 1 is to play A3. And what is the justification for player 2 to play B1? B1 is going to be played because player 1 is going to play A1, right. If player 1 plays A1, B1 is the best response. And why is A1 being played? A1 is being played because player 2 is suppose is believed to be playing B3, then A1 is played. So, you see we are back to B3 here. So, this way it will go on like this, we have an infinite regress that I talked to you about, and each action is being justified on a belief which is dependent on the previous action in the sequence. So, that is why these actions B3, not only B3, here from we can see that B3, A3, B1, A1, all these 4 actions are justified, they are rationalizable. And similarly, we can show that A2 and B2 are also rationalizable. So, this is the definition of rationalizable, and you can see that rationalizability, the actions which are rationalizable, it is related to the idea of best responses, and therefore, we have a result which is the following. In a mixed strategy game, the mixed strategies which survive the iterated elimination of strategies which are never a best response are known as rationalizable strategies. An example is this game itself. Here B4 was never a best response, so we eliminated this, and consequent to the elimination of B4 we can eliminate A4 also, because now A4 is never a best response to any of the actions by player 2. So, A4 and B4 are eliminated, and we can see that none of these other actions A1, A2, A3, B1, B2, B3 can be eliminated. So, they are never actions which are not best responses. Therefore, these A1, A2, A3 and B1, B2, B3 are called rationalizable actions or strategies. Remember, any strategy can also be an action, because in that strategy any particular action is being played with probability 1. So, this is some discussion about rationalizable actions and rationalizable strategies, and what is the upshot of this, that by applying these ideas, that iterated elimination of dominated actions or rationalizable actions, the idea of rationalizable action or strategies, we can pinpoint some action profiles which can be played without any history, because in Nash equilibrium we required a history to justify that a particular action profile is being played, and that is why it is called a steady state. But in case of rationalizability or strictly dominated elimination of strictly dominated actions, we did not need any previous play of the game. We just apply the idea of rationality and the fact that rationality is a common knowledge, and we try to find out what are the action profiles which are left. But at the same time, we also must keep in mind that this is not giving us a tremendous amount of predictive power, because we are left with so many action profiles, 9 of them, and all of them obviously are not Nash equilibria. Nash equilibria will pinpoint us to a very few of the action profiles. For example, to take a simple example, take the case of matching pennies. This was the game, and in this game, by rationalizability, by dominance, we cannot eliminate any of the actions. So, HT by player 1 and HT by player 2, both these actions for each of these players remain there, and so it means that in terms of BO strategies, all these 4 action profiles remain. We cannot eliminate any of them. Whereas, if I apply Nash equilibrium, the idea of Nash equilibrium, I have a unique solution which is half-half, a mixed strategy equilibrium. So, Nash equilibrium has basically it has pinpointed to certain action profile or action profiles, whereas this idea of rationalizability and strict dominance, they do not pinpoint at a very small set, but they take into account a very large set, and in that large set maybe Nash equilibrium, the set of Nash equilibria is a subset, is a small subset. So, predictive, as far as predictive power goes, as far as pinpointing a particular set of actions goes, a Nash equilibrium is better. It is basically condensing the solutions to a smaller set. So, therefore, the idea of Nash equilibrium is powerful and it cannot be thrown away. So, one has to figure out how any game, for example, converges to a Nash equilibrium profile, and one way to do that, how a game converges to a Nash equilibrium profile, which is then getting repeated because of steady state properties, is that people tend to form beliefs because they have seen the previous play of the game. So, beliefs are formed, and this formation of beliefs in a sequential manner leads us to the Nash equilibrium. So, there are 2 hypotheses how the beliefs are formed and we go to a Nash equilibrium. One can be discussed, which is called the best response dynamics, and the second is known as fictitious play. So, let us start with this first one, best response dynamics. In each of these 2, that is fictitious play and best response dynamics, a player start with an arbitrary belief regarding other players' actions. And when after they have started with an arbitrary belief regarding other players' action, after the game has been played, then they observe the other player's action, and observing the other player's action, they believe that this action is going to be repeated by this player in the next stage also, in the next play of the game also, and this happens for each of the players, and this way this game goes on. So, suppose player 1 and there is player 2, suppose there are 2 players only, and player 1 suppose starts with the belief that player 2 is going to take action B1, and player 2 believes that player 1 is going to take any action A1. These are arbitrary, and believing this, they take the action. Suppose this is the best response function of player 1, this, and believing this, he takes the action this. so this is what happens in period 1. After the game has been played, player 1 now observes that B1, the belief that he thought, player 1 belief that he thought of action of player 2 might be different from B to A1, and barring the case of coincidence, B1, small b1 will be different from B to A1, and therefore, in period 2 player 1 now starts with the belief that player 1 starts with the belief that player 2 is going to play this thing. So, this is his now changed belief, and accordingly he takes the action this, and similarly player 2 will now have the belief that player 1 will take this action, right, and therefore he should take this action. All right, and this way the game progresses. Now, it may seem a little naive that the players are just taking the other player's action in the previous play of the game as given and thinking that that action is going to be repeated. That is a simple, very naive kind of belief formation. But nevertheless, in many games, this in fact converges us to the Nash equilibrium. One game in which it leads to a convergence to the Nash equilibrium is the Cournot duopoly case, duopoly game. And I have one question regarding this in fact. Find the sequence of pairs of outputs chosen by the firms in Cournot duopoly game under standard assumptions if both firms initially choose 0. So, here both the firms are choosing the actions 0 0 and the game is starting, and we have to find out what is the sequence of actions taken by both these players, and does it converge to the Nash equilibrium. That is what we want to see. Now, in Cournot duopoly game, if you remember, the best response, if I want to write it for player 1, it was given by this was the best response function. Now, in this case what I need to do is that player 1, when he is deciding his output, he is looking at the output of player 2 in the previous period and believing that to be the output in the next period also. So, there is a time involved here. So, I can write it as t minus 1 and this as t. So, he looks at the output produced by player 2 in the previous period, which is q2 t minus 1, believing that to be repeated in this period, and therefore, q2 t minus 1 is equal to q2 t, and therefore, he is taking the best response according to that, and this I know as the best response function, and that is. One more thing that is needed to be remembered is that they are starting with this initial output level of 0. And remember, the best response of these two players are symmetric in the sense that player 2 also has the same kind of best response function. I did not write that. You just have to replace 1 by 2 and 2 by 1. Now, if the best response function is symmetric, if they are starting from the same output levels, then it means that in each period this will happen. In each period their output levels will be same, right. Now, therefore, I can write this as the following. So, this becomes my function, which is a difference function of first order. If I solve this function, then I can find out, I can chart out what is the trajectory that q1t takes, and that will be the same trajectory of q2t. So, how to solve this? There are two parts in a difference equation, in the solution of the difference equation. One is the particular integral and the other is complementary function. In particular integral, the value remains constant, the solution, this is the equilibrium, intertemporal equilibrium value. So, let us suppose this value is k. So, if I substitute this here, okay. So, which means k is equal to alpha minus c divided by 3. This is number 1. The second is complementary function, and let us write it as any arbitrary function a capital A multiplied by small b to the power t, where a and b are parameters. And if we substitute this in this function, what do we get? Here I do not have to include the constant part. What I get is the following: a b t is equal to minus half a b t minus 1, right, because here the subscript is t minus 1, here it is t. So, from here what do I get is b is equal to minus half, because I can divide both sides by a b t to the power a b to the power t minus 1. So, therefore, CF is equal to q I t is equal to minus half to the power t. So, the complete solution is the following: it is equal to particular integral, which is alpha minus c divided by 3 plus the complementary function t, and we have the information that at t is equal to 0, q1 t is equal to 0, right. They are starting with 0 0 output level. So, 0 is equal to alpha minus c divided by 3 plus 1, because if I put t is equal to 0, this becomes 1. So, which means a is equal to minus of alpha minus c divided by 3. So, q1 t will be equal to this. Now, what is important is that as t goes to infinity, this part goes to 0. As this part goes to 0, which means this part also goes to 0. So, as t goes to infinity, minus half to the power t goes to 0, and which means that q1 t tends to alpha minus c divided by 3. So, we basically converge to the Nash equilibrium, because if you remember, alpha minus c divided by 3 was the Nash equilibrium. The same logic applies for q2 t also, because as we have just figured out that since they are starting from the same output level 0 0 and the best response functions are symmetric, therefore, the dynamics of these two outputs q1 t and q2 t will be same. So, q2 t also will converge to alpha minus c divided by 3. So, in this case, this naive kind of belief that my rival's action in the previous period is going to be repeated by him in the next period, this kind of belief is helpful in this case, at least in this case of Cournot equilibrium. But in also one thing we have not said is that which was there in the question, that what are the sequence of actions, what are the actions to be produced, what are the outputs to be produced by these two players, by these two firms. So, at t is equal to 0, I know the output level is 0. So, that is there. If t is equal to 1, I can put t is equal to 1 here, and I can find out what is the value of output for player 1 in the first period. I can put t is equal to 2, and I can find out the value of output for period 2, etc., etc. So, the sequence can be derived from this equation itself. But in many games this is not true. In many games this kind of naive beliefs will not lead us to an equilibrium. For example, in the Nash equilibrium. For example, take the case of Battle of Sexes. In this game there are two players. And I know these are the PO strategy Nash equilibrium. Now, if I start with an arbitrary belief that player 1 believes that player 2 will play B and player 2 believes that player 1 will play O, then do we get to a Nash equilibrium? If B is the belief of player 1, he will play B, and if O is the player of player 2, he will play O, and we basically reach here. In the next period, what player 1 will do, he will play O and player 2 will play B, and we shall reach here, and again this is going to be repeated. So, we are basically fluctuating between 0 0 and 0 0, that is OB and BO, none of them are Nash equilibrium. So, this naive belief may not be helpful in some cases, and therefore, we need this second concept called fictitious play. Here the beliefs are the following. Suppose I have seen my rival player 2 in the 10 play of the game, he has taken A1 5 times, he has played A2 4 times, he has played A3 1 time and A4 0 times. So, in the 11th play of the game, I shall believe that he will play A1 with probability this, A2 with probability this, A3 with this probability and A4 with this probability. So, I believe that the frequency in which he has played the actions will be proportional to the probabilities he will attach to each of the actions when he plays the next play of the game. So, and I take into account the fact that he can play mixed strategy. Is it helpful? Is this kind of a little more sophisticated belief structure leads us to the Nash equilibrium? Well, the result is the following, that if I have a 2 by 2 structure, that is there are 2 actions and 2 players, and if the interests are directly opposed, which means that if I gain, my rival loses, then this kind of belief structure leads us to the Nash equilibrium. So, take the case of matching pennies. In matching pennies, in fact, infinite play of this kind of the infinite play of the game with this kind of belief structure leads us to the Nash equilibrium, no matter where we start from, that is no matter what arbitrary belief we start from. So, these are some of the attempts that have been made to justify how from point 0 time 0 we converge to Nash equilibrium, and there are lots of works to be done, still to be done in this field. So, this is more or less the module 4, which module was about mixed strategy Nash equilibrium. What we shall do in the next lecture, from the next lecture we shall take up another important topic of game theory, which is sequential games, and we shall see what are the various facets of that game. Thank you so much. First question, define rationalizable strategies. So, let us look at this definition carefully. In a mixed strategy game, the mixed strategies which survive iterative elimination of strategies which are never best response are known as rationalizable strategies. So, we can give some examples. The strategies which are not best responses, they will be eliminated, and the rest will be considered as the rationalizable strategies. So, very simply, if we remember the prisoner's dilemma game, so this was the prisoner's dilemma game. Here we see that for one the action NC is never a best response. So, this is eliminated. Similarly, for 2, again NC is never a best response. So, one is left with CC, is the rationalizable strategies. Here, since it was a 2 action by 2 action game, so the game was simple, but one can of course think of more complicated games where mixed strategies are eliminated, because those mixed strategies are never a best response. Explain how the beliefs are formed and updated in best response dynamics. In the Cournot model, if firms act according to best response dynamics, find the output of firm 1 as a function of its previous output level. So, in best response dynamics, what happens is that players believe that others' actions in the last period will be repeated. in the next period, and accordingly they play according to their best response function. So, whenever they see someone, some other player is playing some action, suppose A1 bar, then player 2 thinks that in the next period also player 1 will play A1 bar, and then she uses her best response function, and suppose this is equal to A2 bar, and so she plays A2 bar. So, this is how best response dynamics works. In Cournot equilibrium model, if the firms act according to the best response dynamics, find the output of firm 1 as a function of its previous output level. So, in Cournot model, what do we know? We know the following. This is the best response function. Okay. Now, remember here we are talking about periods, different periods. So, one has to incorporate the time dimension here. So, let us call this QT1, that is the output of firm 1 in period T. Now, she will decide her output according to the output of firm 2. But this output of firm 2, the output that firm 2 will decide, is not known by firm 1 from beforehand, and this is simply therefore is going to be what was firm 2's output in the previous period, because that is what the best response dynamics tells us. And since the game is symmetric, QT1 is equal to QT2. So, if I simplify this a little bit more, this. So, that is how the output of firm 1 depends on its own output in the previous period. Thank you.